Welcome to another bonus topic in calculus this year, and this is a series of 3 videos all about integration using trig identities. So you can label this first day integrals using trig identity substitution, day 1. Okay, so there's lots of different trig identities we can use. The ones that are going to come into play today are the Pythagorean identities. So let's review what those are. Those are sine squared x plus cosine squared x equals 1. Sing the chorus once. Tangent squared x plus 1 equals secant squared x. Tanning once is the secret, because if you only go tanning one time, you wouldn't want anyone to know about it. And 1 cot is cozy. 1 plus cotangent squared x equals cosecant squared x. Now remember, there's different forms you can write of these also. So if I take that first equation, sing the chorus once, and solve for sine squared of x, what would sine squared of x equal? Well, I'd move the cosine squared to the other side to make it 1 minus cosine squared x. And similarly, what would cosine squared x equal using that first equation? 1 minus sine squared x. You could do the same with the other ones. This one's solved for secant squared already. If I solve for tangent squared x would be secant squared x minus 1. And then lastly, if I solve for cotangent squared x, it would equal cosecant squared x minus 1. Okay, so what could we use these for? Well, obviously, if you have something like the integral of tangent squared, you can replace it with secant squared x minus 1. Same with cotangent squared, and you do know how to take the antiderivative of those types of equations. But how about, when would you use these other ones? Let me show you. So if I said to evaluate, we'll start with the integral of sine cubed of x dx. Okay, so sine cubed, we don't know what the derivative of what gives you sine cubed, no idea. But I can make a substitution and then use u sub if I'm tricky about it. Because isn't sine cubed the same as saying the integral of sine squared x times sine of x dx? Sure, that's sine cubed, right? And then what can I do here? Well, sine squared has an identity. So this would equal the integral of 1 minus cosine squared x times sine of x dx. Now, it might seem that I've made this more complicated, but really I haven't. Because as soon as I have cosines and sines in the same thing, that's a hint to use u sub. Because the derivative of cosine is something to do with sine and vice versa. Now, cosine is the one that's squared, so that's what you want to make u. Because it's like stuff squared. So let u equal cosine of x. Then what's du over dx? Well, the derivative of cosine is negative sine of x. So if I want to solve for sine x dx, which would be the leftover piece here, we'd have that negative du equals that. Okay, so this is the same as saying the integral of 1 minus, the cosine is u now, so u squared, and sine x dx is times negative du. Now this negative is a constant, so that can pull out front. It's going to be negative times the integral of 1 minus u squared du. That's way easier. Now we can do that. This would be negative in parentheses. Derivative of what gives you 1? U, because u is our variable right now. So just u minus u cubed over 3 plus c. And putting u as cosine of x back in gets us our final answer. I'm going to distribute that negative also. Negative cosine of x plus cosine cubed of x over 3 plus c. Okay, that's the answer. So the trick is get it so I can use a trig identity. The trig identities are all squared. Then do u sub, because the leftovers will be the other piece that I need. And then we can just do regular integration. All right, let's try another one. How about the integral? We did sine cubed. Let's do cosine cubed. Cosine cubed of x dx. So same thing, I want to break this up, so there's a squared involved. It'd be the integral of cosine squared of x times cosine of x dx, because that's the same as cosine cubed. Now cosine squared is the same as 1 minus sine squared, still using that first Pythagorean identity. So this would be the integral of 1 minus sine squared x times cosine of x dx. And now I've got sines and cosines. Again, this time sine is the stuff squared. So let u equal sine of x. Du over dx. Derivative of sine is cosine of x. And that's even easier because I just want to solve for cosine of x dx, which would be du. Du is cosine of x dx. Okay, so now this is going to equal the integral of 1 minus u squared times du. And we can take the antiderivative just like before. It'd be u minus u cubed over 3 plus c. Final step is plug that u back in. It's sine of x minus sine cubed of x over 3 plus c. And there you have it. Okay, makes sense? All right, well, did sine cubed and cosine cubed. I'm going to flip the page. Similar, what if I try the integral of cosine to the 5th of x dx? Okay, well again, if I'm going to use those trig identities, I have to have it cosine squared. So if I break this up in cosine squares, it'd be the integral of cosine. Let's try to get that to look a little bit better. Integral of cosine squared x times cosine squared x times cosine of x dx. Right? So I'm just splitting it up so I have cosine squareds involved. That's still equal to cosine to the 5th. In other words, this is the integral of cosine squared of x squared times cosine of x dx. And cosine squared, I can use 1 minus sine squared again. So this is the integral of 1 minus sine of x sine squared squared times cosine of x dx. Okay, so just like before, we can use u sub. What would I let u equal? I'm going to let u equal the stuff. So that's sine again. So let u equal sine of x, which means du over dx is cosine of x. And I want to solve for cosine of x dx over here. So just like before, that's just du. So this turns into the integral of 1 minus u squared du. And we've done stuff like this earlier this year. You need to multiply this out. So if you want to FOIL it or box it, however you want to do it is fine. 1 minus u squared, 1 minus u squared. This is 1 minus u squared plus u to the fourth. So we'd have the integral of 1 minus 2u squared plus u to the fourth du, which turns into u minus 2u cubed over 3 plus u to the fifth over 5 plus c. And finally, I can just plug in sine for all my u's. So it's sine of x minus 2 sine cubed of x over 3 plus sine to the fifth of x over 5 plus c. All right. So a little bit more complicated, but same idea. Now you'll notice that all the integrals I did were sine or cosine to an odd power. So let's just do a quick summary, and then we'll be done with this day. In general, if we've got the integral of sine to the odd power of x dx, or if we've got the integral of cosine to an odd power of x dx, we want to rewrite this as the integral of sine to an even power of x dx times an extra sine of x. Oops, I guess I put the dx in the wrong spot there. Sorry. Or you could do the same with this. You could write this as the integral of cosine to an even power of x times cosine of x dx. That'll always work. You can do something like that. And when you have this sine to an even or cosine to an even, you can do something with a Pythag identity. Just like we did in the last example. Good? Good. Now, also, as a side note, we can use the other Pythagorean identities also. For instance, what if I wanted to do the integral of cotangent squared of x dx? Well, the derivative of what gives me cotangent squared, I don't know. But there were other identities. Cotangent squared of x equals cosecant squared of x minus 1. So I could do that. We could make this the integral of cosecant squared of x minus 1 dx. I'm using 1 cot as cosi. And this may not be an obvious one, but you do know how to do this. The derivative of what gives you cosecant squared of x? Well, it's negative cotangent. You know how like the derivative of what gives you secant squared? Tangent. The derivative of tangent is secant squared. So if you see cosecant squared, that just came from cotangent, but it's negative cotangent. And we did derive that. way back at the beginning of the year. Just one we don't use too much. So that's negative cotangent of x, and then the derivative integral of 1 is x. So minus x plus c. Okay, so there's an easier trig substitution that you can make that doesn't involve u sub. All right, that's the end of day 1 of the notes. If you wanted to start working through this integration using trig identity sheet, you can do number 1 now. Number 2 is one of those signs to an odd power, so you could do number 2. We haven't talked about higher powers of cosine and sine when they're even, so you can't actually do 3 yet. And the other one you can do, as crazy as it looks, you can do number 4. This is just a u sub question. There's no crazy trick. It's just a little bit tricky u sub. So if you have trouble with number 4, let me know and I'll give you a hint. But you can try 1, 2, and 4 based off of what you know so far. Good luck. I'll see you for video 2.